All right, today we're going to pop the hood on the biochemistry of obesity. And we're going way beyond just talking about weight. We're going to explore this whole complex biological story, about our body's amazing energy systems and what really happens when that fuel tank starts to overflow. So let's get right into it.
I wanted to kick things off with this quote. Now, it's not actually about obesity, it's about cholesterol, but it absolutely nails the spirit of what we're talking about today. See, just like cholesterol, the biology behind how we store fat is, well, it's often misunderstood. It's a crucial system. It's not the bad guy. This really sets the stage for us to take a deeper, more scientific, and less judgmental look at what's going on.
Okay, so let's start with section 1 and really define the problem. We're going to look at what obesity means from a clinical standpoint, how it's actually measured, and why it's become such a huge global health issue, one that's tied to some of the most common diseases out there.
So here's the official clinical definition. The two parts you really need to focus on are excess body fat that impairs health, right? This isn't about how someone looks, it's a medical condition. And it all comes down to a fundamental imbalance between the energy we're taking in and the energy we're actually using.
So how do we measure this? Well, the most common tool you'll see is the body mass index, or BMI. It's pretty straightforward. A BMI between 25 and 29.9, that's classified as overweight. But once you hit a BMI of 30 or more, that meets the clinical definition of obesity.
But here's the thing. BMI doesn't tell the whole story. Not even close. What's absolutely crucial is where that fat is being stored. We basically see two main types. First, there's central or android obesity. That's when fat collects around the abdomen. This type carries a much higher metabolic risk. Then you have peripheral or gynoid obesity, where fat is stored more on the hips and thighs. This one's linked to a lower risk. It really is a case of location when it comes to body fat.
But before we dive into what goes wrong, let's just take a second to appreciate how elegant our body's energy storage system really is. I mean, why did evolution pick fat as its #1 fuel reserve? It turns out there are a couple of truly brilliant reasons.
And this right here shows you the first reason perfectly: energy density. Just look at this chart. Fat packs an incredible 9 calories per gram. That's more than double the energy you get from carbs or protein. It's just a ridiculously concentrated fuel source.
Okay, and the second reason? It's all about efficiency. You see, fat is stored without water. It's anhydrous. Carbohydrates, on the other hand, which are stored as glycogen, need about 2 grams of water for every single gram of glycogen. So get this, if our bodies stored the same amount of energy as glycogen instead of fat, a 70-kilogram person would be carrying an extra 55 kilograms. That's insane. What an incredible evolutionary advantage, right? So we've got this brilliant, super efficient system. But what happens when that system is constantly being pushed past its limits? When there's always an energy surplus? Well, that's when all the intricate hormonal signals that keep everything in check start to get their wires crossed.
At its very core, it really just comes back to this simple equation. When the calories you take in consistently outpace the energy you burn, that surplus has to go somewhere. And it gets stored as fat in these specialized cells we have called adipocytes. I mean, that's what they're designed to do, but even they have their limits.
All right, let's meet the first key player in this whole hormonal conversation, leptin. Leptin is produced by your fat cells, and it's basically the "I'm full" hormone. Think of it like a text message that gets sent to your brain saying, hey, we've got plenty of energy stored down here, you can cool it with the eating now. So here's the million-dollar question. What happens when the brain just stops listening? In obesity, a state called leptin resistance can develop. The "I'm full" text messages are still being sent loud and clear, but it's like the brain's phone is on silent, or the receiver's just broken. The brain never gets the signal, so it thinks the body is starving, which just keeps driving that feeling of hunger.
And on the complete opposite side of this hormonal tug-of-war, you've got ghrelin. This one is made in the stomach, and it's the "I'm hungry" hormone. So while leptin is trying to hit the brakes, ghrelin is slamming on the accelerator. Now, in a balanced system, ghrelin spikes before a meal to make you hungry, and then it drops off after you eat. The problem is, in some people with obesity, ghrelin just doesn't drop as much as it should after a meal. This can leave you with that nagging feeling of hunger, even when you've had plenty of fuel, and it just feeds into that cycle of overeating.
And then, of course, there's insulin. We can think of it as the master storage hormone. Its main job is to manage all the fuel coming in. When you're in a state of energy surplus, high levels of insulin are constantly on duty, telling the body, hey, take that extra energy and pack it away into fat cells for later. So let's zoom in and see what's happening at the cellular level. When these adipocytes, these fat cells, get overfilled and enlarged, they get stressed out, they become dysfunctional, and they start pumping out these inflammatory signals called cytokines. This creates this constant, low-grade inflammation all over the body, and that inflammation is a huge driver of all the other metabolic problems that follow.
Yeah, and this low-grade inflammation, it isn't just a small local problem. It sets off a massive metabolic ripple effect. It's like dropping a stone in a pond, and it leads to a cascade of really serious health consequences that can affect your entire body.
And here they are, the major consequences of that ripple effect. The very same inflammation that messes with leptin also drives insulin resistance, which, as you know, can lead straight to type 2 diabetes. It messes up your blood lipids, it raises your blood pressure, it can cause fat to build up in the liver, and it all contributes to this cluster of conditions we call metabolic syndrome.
Okay, let's quickly break down one of those terms, dyslipidemia. It sounds super complex, right? But this table makes it really simple. Basically, in obesity, what we typically see is a rise in triglycerides, an LDL, that's the bad cholesterol, and a drop in HDL, the good cholesterol. It's just a really unhealthy shift in your entire blood lipid profile.
Now, for any of you studying this for an exam, the source material actually has let's call it a memorable mnemonic to help you remember these key consequences. It uses the acronym DILF, which stands for diabetes, insulin resistance, lipid abnormalities, and fatty liver. Look, it's a bit informal for sure, but it's a quick way to lock in that major metabolic fallout.
Okay, so we've seen how this incredibly fine-tuned system can be thrown so far off balance. The logical next question is, of course, how do we start to rebalance it? Well, the clinical approach is actually pretty multifaceted and very structured. The way management works is with a tiered approach, kind of like a ladder. The foundation, step 1, is always lifestyle changes. That means diet, physical activity, and behavioral therapy. If those aren't enough, you might move up to the next tier, which could involve medications. And then, for severe cases, the final option on the ladder is surgical interventions, like bariatric surgery.
And this brings us right back around to that critical point we made earlier about where the fat is stored. This quote really hammers home why it's not just about the total amount of fat, but its location. Central obesity, which we can easily measure with a high waist-to-hip ratio, is what poses the biggest risk. Recognizing that pattern is exactly why getting in there with early and effective intervention is so critical for a person's long-term health.
So let's quickly recap the biggest takeaways from our explainer. Number 1, obesity is a complex metabolic disease, not just a matter of excess weight. Number 2, it all starts when this brilliant, evolutionarily perfect energy system just gets completely overwhelmed. 3, this breakdown causes hormonal signals like leptin to go haywire, which kicks off a whole cascade of nasty consequences. And finally, number 4, managing it isn't a one-size-fits-all thing. It's a structured process that moves from lifestyle changes all the way to medical intervention.
So we'll end with this question to leave you with. Our understanding of the genetics, the hormones, the cellular mechanics of obesity is growing every single day. And as we continue to decode this incredibly complex biology, it raises a really exciting possibility. Will the future of treatment move beyond these general guidelines and become more deeply personal than ever before? Definitely something to think about.